Good day, everyone. Welcome to Marinay's Powerhouse Team Review and Training Center. My name is Engineer Reggie Marinay. So, you can call me Kuya Reg, no, to our Filipino viewers. We also welcome our non-Filipino audience, no, or students, if there are. Maybe someday they would watch this video because we are going to upload this video in our YouTube channel, no? So, this is the name of my YouTube channel, Reggie Marinay YouTube channel, no? This YouTube channel is for our Filipinos and even non-Filipinos. If you are American, African, European student, no? Whoever you are, no? As long as you are electrical enthusiast, okay? So, this YouTube channel is for you, okay? So, today, we are going to discuss DC circuits, direct current circuits, part 13, entitled Source Transformation, part 1. To our non-Filipino audience, so please bear with us. Okay? I don't have an English tongue because I am a Filipino. So from time to time, I will speak English. I will have my statement in English, and then from time to time, I will convert it in our language in Filipino. Okay, but don't worry. We will try our best for you to understand this lesson, even if you are American or European, no? You have that English tongue. Okay, then I have to apologize because from time to time, maybe my English grammar could be wrong, no? Maybe wrong. Okay, so please bear with us. Okay, so okay, let us discuss now our topic, the source transformation. So let us go on the board. Source transformation, actually this speaks about the Thevenin's equivalent circuit, and we have the Norton's equivalent circuit. So we can convert these two. The Thevenin's equivalent circuit that contains the VTH or the open circuit voltage in series with the open circuit resistance, RTH. And then these are the two points, okay, the two terminals where our load resistance are connected. Okay, so our IL is simply by Ohm's law. So this is VTH, then all over RTH plus RL. Okay, this Thevenin's equivalent circuit can be converted into Norton's equivalent circuit. So the Norton's equivalent circuit is a circuit that contains a short circuit current. Okay, basically this Norton's current is a short circuit current when we remove RL and we put a short circuiting conductor at terminals A and B. What will be the short circuit current to that short circuiting conductor? Okay, so our Norton's current, this is our short circuit conductor. In the other book, they uses this symbol, the ISC. So meaning that is the short circuit current. That is basically equal to the Ohm's law, that is VTH then over RTH. So considering our Thevenin's circuit here. So VTH then over RTH. Okay, in getting our load current, so this is our load current. Our load current simply equal to, by current divider theorem, so we have here, the resultant current is our I sub n. So that is equal to I sub n. Okay, this is the resultant current. The resultant current is the current that will be entering to our node because the Rn and RL are now connected in parallel. Okay, there are two common nodes for a parallel circuit. This is the upstream node and the downstream node. Okay, I sub n is the current approaches to our upstream node, and it is also the current leaving to our downstream node. So this is considered to be the node, okay, because these two are connected in parallel. Now, what is the value or what is the formula in getting the IL? So our IL simply equal to, so this is our I sub n, that is the resultant current, multiplied by the opposite resistance, we have the R sub N, divided by the sum of the two resistors, R sub N plus RL. Okay, there you are. Okay, now, we said that our I sub N is VTH over RTH. So we can substitute here. So this is our IL that is equal to, so we have VTH then over RTH. Okay, RTH. But take note here that our RTH is also equal to our RN. Okay, they are just the same. Now, if you are getting the values, how we calculate our RTH and RN, they are just the same. Totally, they are just the same. No? There's no difference between these two. Okay, it's just that designation. That's the only way they are different from each other. So, our IN is equal to VTH then over RTH. So, I will just replace the RTH with RN since they are equal. And then we have here our Rn, then all over Rn, then plus we have RL. Okay? And then the Rn will cancel out. Okay? Then our IL is equal to, so this is our VTH, then over Rn plus RL. Okay? So this will be the equation of IL is equal to VTH over Rn plus RL. So, we can see here that this is actually the current for the Thevenin's equivalent circuit. They are just the same here. VTH over Rn plus RL. No? VTH over RTH plus RL. Okay? So, we may replace this Rn by RTH since they are just the same. Okay? Now, let us solve our problems. The first problem here, this is for number 1 to 3. This is our first problem set. Okay, we are given here a 15-volt source. Then we have a 5 ohm resistor is connected with a 15-volt source. So we have our RL that is 10 ohms. Okay, the question here, so I already write the given for this problem. So we have 15, 5, then we have 10 ohms as our RL. Okay. First question is, find the current source equivalent of the circuit shown. Find the current source equivalent. In here, we are seeing here a Thevenin's equivalent circuit, meaning there is a voltage source, there is a series resistor. Okay? What is the current source of the equivalent? Current source equivalent of the circuit shown. Okay. So, basically, that is our I sub n. So, I sub n is equal to, okay, so that is equal to, so if you are to consider this is VTH and this is our RTH, so it's simply by Ohm's law, so we have here 15 over 5. So, simply the answer is 3 ampere. Okay? Okay, that is our answer, 3 ampere. So, the answer would be letter A. Okay? Then let's have number 2. Find the load current. So, we are asked to find the load current. Okay, this is for number 1. Then for number 2, we are asked to find the load current here. This is the load current. Okay, let us have a Norton's equivalent circuit here, so that you will see the principle. Okay, the Norton's equivalent circuit. Okay, the Norton's equivalent circuit, so we have here a current source, the load resistor, we have here our 10 ohms, Okay, then we have here our parallel resistor. This is our short circuit current. This is our I sub n, which is equal to 3 amperes. This will be our Rn. Our Rn simply equal to 5 ohms here. Okay? So we can put here 5 ohms. Okay? And then this is our load current here. Okay, we can solve this directly. So this is by current divider theorem. Current divider theorem. Okay? Our IL by Norton's theorem, our IL simply equal to the resultant current, which is equal to 3 ampere multiplied by the opposite resistance. The opposite resistance is 5 ohms all over 5 plus, then we have here 10. Okay? So what will be our IL? Okay? So we have here 3 times 5 is 15 over 5 plus 10, that's also 15. So therefore, the answer is only 1 ampere. That is our IL. Okay? Our answer is letter D. Okay? So, let us have now number 3 problem. Find the load voltage. Okay? Find the load voltage for number 3. This is very easy. I'll just put it here. So, we have here our load voltage, VL. So, our VL basically is the voltage at the load here. Okay? Simply equal to IL multiplied by RL. So, our IL is only 1 ampere times 10 ohms. Okay? Calculator, 1 times 10. Okay, by the way, it's just 10 volts. Okay, that's very easy. Okay? So, ang dali lang, no? So, kayang-kaya, mga kawerpa. So, the answer is 10 volts. Okay? And then, let's have now this problem for numbers 4 to 6. Let's go with the second problem set. Here. So, in here, we have, okay, please close up this portion. So, we have here our 72 volt source. We have a 24 volt source. Okay? And then, this is our load resistance. That is 6 ohms. Okay? So, the 72 is in parallel with the 9 ohm resistor. The 24 volts, it has a series resistance of 3 ohms. Okay, let us find the following. But first, I will draw our circuit. I will redraw our circuit for numbers 4 to 6. Okay, so basically we have a two-loop circuit here. Okay, we have here 72 volts. Okay, we have 24 volts. Then we have 9 ohms. We have 3 ohms. We have 6 ohms. This is our RL. It's equivalent to 6 ohms. Okay. Then, of course, our load current, that is one of the unknown. That is our load current here. Okay. Let's have question number 4. Okay, let's go over with question number 4. Find the total or the Norton's current in the circuit shown. What is the Norton's current? The total Norton's current. So, we have here a Thevenin's equivalent circuit. We have two Thevenin's equivalent circuit. I'll show this with you guys. So, these are the two Norton's equivalent circuit. That is the first one, then this is the second one. Okay. So let us convert this by its Norton's equivalent. Okay? So the first Thevenin circuit, so let's say these are the 2 points. We have the 1, 2 points. Okay? Let's say these are the 2 points we draw. So there will be a short circuit current. The short circuit current is going upward because we follow the conventional flow of electrons. What is the conventional flow of electrons? Again, okay, from our electrical principles. Okay, this is our current that is going upward. It should live on the positive terminal of the battery, then going to the negative terminal of the battery. I mean, the conventional flow, if we want to become more specific, the conventional flow is externally, that is from positive to negative, externally. But internally, meaning inside the battery, no, sa loob ng battery natin, so we have here from negative to positive. Okay? What's important is we have this current that is leaving. No, doon siya lumalabas sa positive terminal ng baterya natin. No, it lives on the positive terminal of the battery. Okay? So, we have this negative and positive, so that is going upward. If our battery, shall we say, is in reverse polarity, what do I mean? If our battery is like this is negative, this is positive, meaning our current must be going downward. Because the idea here is this current must leave the positive terminal of the battery externally. It must leave on the positive terminal. Okay? If you have a battery like this, that the current is going downward. If your battery is connected like this is negative and positive, so the current is going upward. That is why the current here is going upward. And then, what is the value of this current? What is the value of this current? Shall we say, this is I, Norton's current 1. Simply by Ohm's law, we have 72 over 9. What is 72 divided by 9? So that is simply 8. I think the 5th grader will beat me here. Okay? You see, I told you before that you don't have to be a great in mathematics if you want to become an engineer. What's important is you have mathematics in your heart. Okay? Let the calculator do that thing. Okay? So, of course, that is not that nice to be very dependent on the calculator, of course. Okay? It is a very big advantage on your part if you have very good in mathematics. Okay. So, 72 over 9 is 8. So, this 8, that should be 8 amperes. 8 amperes. Okay. So, we already have here 8 amperes. See? And then, what is this resistance? This is our Norton's resistance for this particular Thevenin circuit. So, just copy that one, 9. Kopyahin mo lang. That is 9 ohms. And then, the 2 point, then we have here our load resistor, our 6 ohm resistor, this is our RL, is equal to 6 ohm. And then what about on the right side? This will be the equivalent Norton circuit. The Norton's resistance on the right side. And then the current source. What about IN2? Okay, by Ohm's law, take a look here. 24 divided by 3. Okay? So the answer is 8 amperes also. Okay? Also, they are 8 amperes. So put here 8 amperes. Okay? What about the resistance here? The resistance here is the same as the 3 ohms. Okay? So just copy that. Okay, as we see here, so we have a 24 divided by 3. That is our Norton's current on the right side. And then the 3 ohm here, just copy this 3 ohm resistor. Just copy that. Since the Thevenin's is equal to the Norton's resistance. And then we have our RL, the 6 ohm resistor. Okay? Take note that we have our load current here. Load current. We are seeing here a purely parallel circuit. Okay? That is a purely parallel circuit. Now, we are going to have our Norton's equivalent circuit. Let us have our Norton's equivalent circuit. Okay? How to do it? So our Norton's equivalent circuit, of course, we have our current source here. Okay, this is our RL. That is equal to 6 ohm. And then our load current here, okay, let us have first our Norton's resistance here. Then we will solve the Norton's current. Let us have first our Norton's resistance. Take a look here. So the RL is just this portion. This is our RL. This is also our RL. And then we have these two resistances. 1, 2. We can see here that the 9 ohm is in parallel with the 3 ohm resistor. So what we are going to do is 9 times 3 over 9 plus 3. 9 times 3 then divided by 9 plus 3. So the answer would be 2.25 ohms. Okay? That will be our Rn. Actually, that is one answer. But take a look here. We are going to solve the total Norton's current here. It's actually the equivalent. Let's say that is our total Norton's current. Take a look here. If 8 ampere is going upward, and then this 8 ampere is also going upward, so meaning, always take note, no? It's just like getting the forces. It's like in physics or in engineering mechanics, that if the forces is upward, that is considered to be positive. If the forces is downward, that is negative. Okay? Pag pataas, positive. Pag pababa, negative. Okay. So as we see here, both are 8 amperes. They have the same direction, which is upward. Therefore, that is positive 8, then plus 8. 8 plus 8, that is 16 amperes. So that is our answer. Well, if it so happen that this 8 ampere is upward and then this 8 ampere is going downward, therefore 0 ampere. There's no current. So we have to consider the algebraic sum. Okay? So the answer is 16 ampere. Take a look here, guys. So the answer would be letter B. Okay? Letter B. Okay. Let's go now with problem number 5. Problem number 5, find the Norton's resistance. Actually, we already have this value. Okay? Nauna na. So this is number 4 and then this is number 5. Okay? Which is the parallel combination of the 9 ohm and the 3 ohm resistor. Okay? So we have 2.25, which is letter C. Okay? So that is letter C. Let's have now for number 6. For number 6, find the load current. What is the load current? Again, for the load current, okay, that is equal to the Norton's current, which is equal to 16, multiplied by the opposite resistance, which is Rn. Our Rn is 2.25, all over 2.25, then plus 6 ohm. And our IL now will be equal to our answer is 4.36 amperes. 4.36 amperes. And that is letter, okay, the answer is letter B. Okay, guys? Then let's go now with problems 7, 8, and 9. Okay, so we have this quite a complicated circuit. Okay, for number 7, 8, and 9. Okay, you may copy first our circuit, guys. Okay, let us continue. So here we are given a 3 ampere I1 current source. Independent current source is in parallel with the 4 ohm resistor. And we have I sub 2, 4 ampere is in parallel also with the 2 ohm resistor. So basically we have two Norton's equivalent circuit, the upper circuit and the lower circuit. So, well, they are just connected in parallel here. Okay. So we can have this portion first, then this another portion. Okay. Then we have here our 6 ohm load resistor. Okay, I will draw right away the equivalent Thevenin's circuit for the upper portion. Okay, this is very easy. So please take a look this one. Okay, what is the Thevenin's voltage? That is simply the product of the current here multiplied by the resistance. So therefore, we have here 3 times 4. What is 3 times 4? So that is 12. Okay? So put here a 12 volt source. Okay? By the way, the resistance, you just copy the resistance here. Okay? So we have here 4 ohm resistor. Okay? Say this is the 4 ohm resistor. Okay? Then we have a series voltage here. Again, what is the series voltage? 3 times 4, so we have here 12 volts. 12 volts. Then considering this point, okay, so we have this point, let's say, this is the point, okay, let us have the resistance again here. What is the value of this resistance? Just copy this 2 ohm resistor. This is the Norton's resistance. That is just equivalent to the Thevenin's resistance. So I will just copy these 2 ohms. So put here 2 ohms. Okay? And then, what will be the voltage here? What is the voltage? The voltage is 4 times 2. What is 4 times 2? So we have here 8 volts. 8 volts. Okay? 8 volts. Okay? Let us consider the upper point here and the lower point. These are the 2 points here. Okay? The upper point and the lower point here. And then they are connected with the 6 ohm load resistor. So this is our RL that is equal to 6 ohm. Okay? Wherein that is connected to terminals A and B. So let us put the 2 terminals A and B. This is terminal A, this is terminal B. Then this is our IL. Okay? Then we can have now our Thevenin's equivalent circuit. Okay, how to do it? So, okay, we have a series resistance here. Then our point A, this is the VTH. Then this is our RL. Okay, that is equal to 6 ohms. Then, what is this resistor? This resistor is simply the addition or the total of 4, and 2. They are just connected in series. Please take note, they are just connected in series. 4 plus 2, so we have here 6 ohms. Okay? Then, what about now the 2 voltages? Okay, by the way, why is that these 12 ohms, we have the positive here and we have the negative here? Because the current I1 is upward. We said before that this is the 3 ampere. And also the 4 ampere is going upward. Okay? Pataas sila parehas. So, if we have a 12 volts, this will deliver a current going upward. It's just the same with your 3 ampere source here. That is going upward. What about the 8 volt source? Also going upward. We said before that we are following the conventional flow of current. That the current must leave the positive terminal of the battery Okay? This is positive and negative. Dapat lumalabas siya parati sa positive terminal ng baterya. Okay? It always live on the positive terminal of the battery. Well, if it so happen that our 8-volt source here is like this one, negative and positive, so, well, your current source must be downward because it must live on the positive terminal. Okay? The positive terminal. Okay? So, since they have the same direction, we can see here that these two batteries are connected in series aiding. Always remember that there is a connection of the battery. A battery in series, they have two types. Let us discuss. The batteries in series, we have what we call the series aiding. Series aiding. What is this series aiding all about? So, if we are to trace our 8-volt source, negative, positive, then this positive is connected to negative of 12 volts. Negative, positive. So, this is 8 volts and this is 12 volts. If you have a voltmeter to measure the voltage here, if you have a tester or multi-tester, what will be the voltage here? That is series aiding. So, why is it aiding? Because they help each other. They aid. See? Like Metro Aid. They help us. They aid. Meaning they help. Okay? So, they have the same direction. See? If it so happen they have the same direction, well, it's simply by Kirchhoff's voltage law. Here, it leads, let's say we have a circuit tracing. Even we apply the Kirchhoff's voltage law, the circuit on a clockwise direction. So, let's say by KVL, by Kirchhoff's voltage law. So, we have here, the circuit tracing lives on the positive of 8 volts. That's why 8 volts, positive. And the circuit tracing lives on the positive of 12 volts. That's why that is 12 here. Positive 12. Okay? Okay? Then, if it so happen, we assume this is negative, this is positive of the battery. Okay? So, the circuit tracing lives on the negative terminal of this battery. So, this is negative V. Negative V. So, that is equal to 0. Let us transpose our V here. So, therefore, our V simply equal to, that will become 8 plus 12, that is equal to 20 volts. The reading here will be 20 volts. That is the series aiding. This is actually the principle of a transformer's polarity. The transformer. Okay? Okay? So, let's say we have a transformer here like this one. This is the application. One of the applications. So, let's say we have this transformer. It has a polarity mark like this. So, let's say we have here 8 volts transformer. We have the 12 volts. The coil voltage. Well, of course, if you have a voltmeter here to measure the voltage, that will give us 20 volts. Remember that the positive polarity in the battery, this is what we call the polarity mark of the transformer. That is assumed to be positive at a certain instant. So this is assumed to be negative, positive, negative. Although our transformer is an AC device. But this is just an assumption that at a certain period of time, we assume that this is positive. The polarity mark. You see the dotted mark here? So nakita nyo yung Nora Honor? No? You see Nora Honor? Yung tuldok, nunal. Okay? Ito yung nunal ni Ate Guy. Okay? Mga kawer pa. Okay? Ito siya. So, see this one? Okay? Just the same principle. Connecting transformer coil in series, batteries in series. The same principle. Then what about, sir, for the series opposing? What is series opposing? Okay, I will just put it in here for the series opposing. Okay, I will make use of our sample 8 and 12 here. If it just so happen that this becomes negative positive and this is positive negative, what will be the reading of our voltmeter here? I will assume this is negative, this is positive. This is our 8 volts, this is our 12 volts. The polarity is in reverse now for the 12 volts source, the 12 volts battery. So, binaliktad natin yung 12 volts na baterya, mga kawerpa. So, negative, positive, positive, negative. So, I will have the Kirchhoff's voltage law. It's like that one, by KVL. Okay? This is what we call the circuit tracing. It lives on the negative terminal of voltmeter, that is negative V. This lives on the positive terminal of 8 volts, therefore positive 8. This lives on the negative terminal of 12 volts, so that is negative 12. So that is equal to 0. 0. Okay? Negative B. Okay? So we have here 8 minus 12, that is minus 4. Okay? So I will transpose the negative B. That will become negative 4 volts. By magnitude, it is 4 volts. Okay? So that will become a negative 1. No? Negative. Meaning, this will just have an equivalent circuit. This is negative 4. So this will give this circuit following which voltage has the higher value. 12 volts compared with 8. So this will follow this connection. Why is it called they are opposing? Because the current for 8 volts, it must live on the positive terminal. And also this, the 12 volts, it lives on the positive terminal. They oppose each other. Okay? You see? Just like the opposition in a country. Okay? They always oppose. Okay? Each other. Let's say there are two political parties. Okay? They oppose each other. Okay? Pag mainit ang ulo niyong dalawa, huwag kayong magsasabay. Okay? Okay? So, you see? They oppose. One is going to the right. And this is the leftist. Okay? Going to the left. Wherein the aiding only has one direction. If you help each other, you only have one direction. Okay? But if you oppose, somebody opposes you, there will be two directions. Okay? This is going to the right and this is going to the left. So, whoever has the higher voltage, just like here, the 12 volts, this will follow, this will prevail. Meaning, this is the positive, this is the negative. That will prevail. The connection of the 12 volt source will prevail. So, we have here 4 volts. That is a 4 volts. So, if we have a voltage source here or a multi-tester or a voltmeter, negative, positive, well, it's just the same as saying this is the Kirchhoff voltage law. It lives on the negative side, that is negative B. It lives on the negative of the battery, that's why negative 4, that's equal to 0. So therefore, the circuit is like this one. Okay? What happens, sir, if they have the same voltage? What will happen? Take a look. What will happen if they have the same voltage? Let's say we have here, in any value, if they have the same value, okay, let's say you have your 12 volts battery here. You have another 12 volts, but they are in opposite direction. See, one is going to the right, and the other one is going to the left. So they oppose each other. They have equal power. Okay? They have the same, just like in boxing. Equal number of punches, equal score, so therefore, the fight is draw. Just like the Manny Pacquiao and Marquez fight. It was a draw. There was a draw here. But you will have here a 0 volt. What do I mean 0 volt? Because if you have a Kirchhoff's voltage law here, see, take a look here. If we have a Kirchhoff's voltage law, as you see here, this will leave the positive terminal of this 12 volts. So therefore, this is positive 12. And this is negative 12. Okay? So if we have a positive 12 minus 12, okay? So let's say this is the negative, this is the positive. Minus B, that's equal to 0. Therefore, 12 minus 12, calculator, 0. Minus B is equal to 0. Therefore, B is equal to 0. And what is a 0 voltage? What is a 0 voltage? A 0 voltage is a short circuit that is shorted. That is a very, very dangerous thing to do in a battery or even in transformer. If you connect a transformer that has, let's say, 220 volts, 220 volts coil, no? You see, like this one, that one, this is the polarity mark, okay? They have the same value, let's say, 220, this is 220 volts coil, then your voltmeter reading here will just become 0. And that is a very dangerous voltage, 0 volts. A 0 volts is a short circuit voltage. Remember that. Okay? That is a short circuit voltage. Take a look here. Take a look here. If we have here a 220 volt source, 220 volt source, these are the two terminals. I will put a voltmeter here. What will be the measured value of this voltmeter? Of course, sir, it's 220 volts. That's correct. Because the source is just in parallel with the voltmeter. But if I am going to short the two terminals here, kung shorted yan, mga kawerpa, what will happen? That is 0 volts. 0 volt. No? Magsi-0 na lang yan, mga kawerpa. No? 0 yan. So meaning, it is a short circuit. Short circuit or a shorted circuit. Okay, I'll make it short circuit. Well, the short circuit voltage actually, the voltage becomes so low. It's a very low. Okay? Until it approaches to 0 or a very minimal voltage. That is a short circuit voltage. Okay? Okay, where are we now? Okay, we're running quite fast. So where are we now? Okay, I will put the value for the Thevenin's voltage here. Okay? What is the Thevenin's voltage here? Since the 8 and the 12 volts are aiding each other, so therefore the voltage is 20 volts. So I will put here 20 volts. See? The voltage now is 20 volts. Okay? So let us have the choices here. The Thevenin's voltage is 20 volts, letter A. See? So we have the 20 volts. Then we have here, find the Thevenin's resistance. Our answer on the board is 6 ohms. That's correct. Letter C. And then, find the load current. Okay, so what is then the load current? So this is our load current, guys. Considering our Thevenin circuit here, so this is our load current, IL. Okay? That is our load current, IL. This is as simple as Ohm's law. Okay? No need to memorize the formula. Take a look. What's important is the concept. It's the principle. So, what is the total voltage? 20 volts. What is the total resistance? So, we have here 6 in series with the 6. So, therefore, it is 12. Therefore, our load current is equal to what? 20 divided by 12. That is 1.67 amperes. Okay? That one. 1.67 ampere. And the answer would be letter C. Okay? This is our answer. Letter C. Okay, so, well, that's the end of our part 1 of our source transformation. Okay? Uh, we'll have the part 2 of the source transformation. Okay? So, I'll see you on the next video. Thank you.